Okay, thank you everyone. It's a great pleasure to be here I traveled all the way from Germany here, and it's a great pleasure to be here in San Jose and in Silicon Valley, where all the big players, for example, reside, which we only know from browsing the web or connecting with friends. So actually this is, okay. Actually this is our first bigger research project in the area of NFV, which is actually in total a rather new research area. And I will give you a small overview of our topic today. Well, first of all, one very big challenge of NFV is to reach the performance we know from the big boxes, the big appliances. Actually, this is caused by the virtualization overhead on the one hand, which is, for example, incurred by the actual packet forwarding path in the hypervisor. And also, which is often forgot, is that we have to compete with hardware acceleration. The big appliances that are used for high performance packet processing are often using ASICs, NPUs, and FPGAs. And with this, they often achieve line rate or guaranteed delays. So common approaches to avoid this are to scale out, so to put the actual network functions, instances of the network functions on multiple nodes. But obviously, this requires more rack space, hardware, and energy. Another approach is the reduction of virtualization and the I/O overhead, which is, you probably all know DPDK, but ClickOS, I think in the research area, it should be also, the ClickOS platform should be also known. And a third idea is to use hardware acceleration. Well, here we see, of course, simplified architecture of a big appliance, of a hardware-accelerated appliance. Here we have a CPU that does all the management and several ASICs, NPUs, or FPGAs, depending on the actual appliances, which do the actual workload processing part. Yes, from this we can say hardware acceleration has the opportunity to supersede the I/O performance of standard processors like x86 or ARM. In terms of line rate and guaranteed delay, the question is, can we somehow improve NFV with hardware acceleration? Well, actually this is not something very new, but we have another question if we want to make it more precise. What about combining virtualized network functions on standard processors with network-attached acceleration hardware to fulfill a common task? So on the one hand, this solution should be elastic, so that the network function we use can dynamically acquire and book acceleration hardware depending on the performance needs. And it should be network attached. This means this is a requirement actually for being able to pool acceleration hardware resources in a whole data center. Well, what do you mean with acceleration hardware? What is it? First of all, we have the ASICs. These are chips, integrated circuits designed for a very, very special purpose. They actually deliver the highest performance we know, but the drawback of them is they are not reprogrammable for a different use case. So these ASICs are actually not used in our idea, in our solution. First of all, we have the FPGAs. These are reprogrammable, so thus they are more flexible. They have a slightly lower performance, but the custom logic we can define on them actually delivers a very high performance still. And the feature that is, it's not totally correct that this is some kind of virtualization, but it's somehow comparable with it. We can share the resources on one FPGA with a feature called partial reconfiguration. Then we have the network processors. These often have many cores that are connected through high bandwidth buses, and they can actually they actually improve their performance by using parallelization and pipelining. And then we, of course, have the graphics processors, which have the single instruction, multiple data, idea to offload, to have high performance. Well, this is a finding where our work is based on, actually, that an NPU, if we have a simple use case, an NPU is very high performant. But actually, the performance decreases with use case complexity. And so we conclude the work of an NPU should have a simple use case. And we seek an opportunity to have a hybrid general purpose processor and acceleration hardware architecture. So, in a scenario where a network function is only slightly utilized, where we have low performance needs, we use the classical NFV approach by running the virtualized network function completely on a general purpose processor. When the utilization, the performance needs increase, then we offload a simple use case to acceleration hardware. We dynamically book, we dynamically acquire from the platform. Open flow or OFPI switches then split the use case to a simple part and a complex part. So what do we mean with simple and complex part? We have to define this specifically for each network function. For example, the network function of a PPP or PPPoE access concentrator, there the discovery, authentication, billing, or any database part could be conducted on a general purpose processor, while the acceleration hardware only does the session stage. Then an IPsec endpoint is likewise, but we have to, of course, we have to do some encryption and authentication stuff on them also. Okay, likewise for the session border controller and the CDN cache. This is a rather difficult slide. So we have the use case complexity versus the performance here. We have some very complex use case that only uses a little performance, and we have some simple use case that uses higher performance. If it is if the workload is rather low, then we can conduct everything on the general purpose processor. Well, if the performance requirements now increase, then we offload the simple use case part onto acceleration hardware, and we even can book multiple instances of acceleration hardware to conduct this use case. Well, all of this should happen in a seamless transition phase between these states. Okay, a network function is commonly shipped as a VNF, as a VM image, for example, C, Python, or processor bytecode, and is doing the complex and simple use case in this standard processor. In our solution now, we additionally deliver offloading programs that have hardware description languages for an FPGA or NPU code. And this is our architecture we want to use. Basically, it's a default NFV cloud platform like OpenStack, and we also have an SDN controller here, and we require an SDN data plane. This is important. What is new is we have these acceleration hardware modules in our architecture, and these modules are actually consisting of one or multiple acceleration hardware processors like FPGAs or NPUs with dedicated network interfaces to the SDN data plane. Well, their duties are to manage their acceleration hardware resources and handle control plane communication with the NFV cloud platform, for example, to acquire, to release the booked acceleration hardware resources. Physical configurations of such an acceleration hardware module could be a PCIe card on the actual hypervisor, but still shared among all hypervisors, a standalone physical node, to put into a rack, or it could be included in an open flow switch. Okay, let's do a larger example. This is a traditional NFV cloud platform where 3 example network functions only have a low performance requirements currently. They all run on their nodes, maybe multiple run on one node only. Now, if the performance requirements increase, we have to scale them out to multiple nodes. So here you can see the virtual PPPoE is now having high performance requirements, and we scale them out here. In our architecture now, we have an additional rack with, this is just an example how to do this. It's additional rack with acceleration hardware. And here, if the performance requirements are now high, we have the virtual PPPoE that acquires some of these resources and then configures them accordingly. Actually, this can be a proprietary interface of the network function. If the network function is proprietary, if it's open source, of course, it's open source. But this is highly coupled, this configuration. This can be highly coupled. Okay, but this solution also is very elastic. So if the virtual PPPoE, now the performance requirements decrease because the customers do something else now, for example, use the VIDS more, then this acceleration hardware can be released and acquired by the VIDS. Okay, current and next steps. Currently, we are doing the prototype implementation. I will come to this later. But as the next steps, we will investigate the problems and parameters of the use case separation. We have to make a seamless state transfer between running a network function simple use case on a general purpose processor and acceleration hardware. Also, the network delay between the general purpose processor that configures acceleration hardware can be a serious issue. So between a session there can be this can last several milliseconds, and this is very important that we do this in a stable way. Also, the question might arise if we use something like FPGAs or NPUs, it is still open. So actually all the FPGA vendors use VHDL or Verilog, so we have a common description language. We have to define common interfaces and constraints now, so that a network function developer can develop on one VHDL or Verilog platform, and just the bitstream generator for the FPGA is then proprietary. Maybe even this component can be open in the future. But we can have 300 different hardware vendors, and they could all run on one NFV platform. The prototype implementation, I already talked about this. We're currently, this is, for example, a first acceleration hardware module. It's based on a net FPGA card. It only needs a very small coprocessor like a Raspberry Pi or any other small PC to do the management with the cloud platform. Okay, that's it from me, and I'm open to questions.
For your hardware offload acceleration, have you investigated ODP APIs as an interface from the GPPs down to do that offloading?
That's great.
ODP, Open Data Plane APIs, no? The whole genesis behind ODP, right, is to provide, these hardware acceleration engines that are sort of, can be hidden, yet, can do their thing and then be available to the GPPs. So you have services and you're trying to change services, but you have latencies and quality of service you need to maintain. You can send those through, you can leverage your ODP interfaces. Does that make sense?
Yeah. So, in our interface, the network function can completely define the code for the, for example, the logic. Is this also possible with the interface you speak of?
So the world wants generic hardware to run things. Right?
Yeah.
And what you're offering is not, what you're talking about is really the interim period where we're at right now with everything, and that is there's all this hardware out there that
Yeah.
can generate, that are appliances, and then there's this mixed mode.
Yeah.
So this hybrid
Yeah.
sort of presentation is what you haven't said, which I'm saying is very intriguing for this interim period, because we're finding that you'll be tracking into the hypervisor. You want to stay out of the hypervisor for these latencies. I just was wondering if the academic presentations here have all been sort of focusing on just getting the job done or investigating and looking at things, rather than maybe looking at the future, which is.
So you mean you see a problem with openness in this architecture? So because we are going away from a common architecture like x86, or?
No, I think it's the way the world is right now.
Yeah.
And I think that if you're going to look at things, I'm just wondering if you had thought about in your research to look at ODP way to interface, or maybe a DPTK way. DPTK doesn't lend itself as much as ODP does, but to these hardware engines.
Yeah.
Because we see a period, right, with all these network services where you can't just throw them all over the GPP, because you're not going to be able to get through these latencies, right? So,
yeah.
I'm just, I'm a straight man. I'm trying to think about what.
What they're doing in the net with the FPGA approach, I mean, it could be easily applied to ODP. It's just conceptually, they're not following the APIs of the SDNet or improvise, but it's there. We're showing that you go to the hardware.
Okay, so we can take this offline. Are there any other questions for Leonhard? So let me ask you this. From your perspective, whom do you see quite active from the chip makers in the hardware acceleration for NFV?
Actually, there is some work. I have a backup slide for this. Where it is? No. Okay. Here, actually, there's SDNet from Brebner at Ali. It's from actually from Xilinx, and they have a small concept on this to have some kind of flexible data plane on open flow switches. It's related to this, yes. On our platform we use the Net FPGA. It's based on a Xilinx Vertex 7, but also we try to keep it open so that other vendors like Altera could be used here.
Okay.
Maybe. Okay.
Great. Any other questions? I guess not. So, all right, thank you so much, Leonhard.